department. Yeah, this talk has sort of components in from all sorts of people, but I particularly want to mention Dirk Kennan and Dan Drew, postdocs with National Grid, who are sat in the audience here, Phil Coker as a lecturer in the School of Construction Management, and there's a whole bunch of other people who have contributed to this over the last couple of years. So, before we start, I just wanted to go back and just reflect a little bit for a moment on the title of this workshop, which is the Management of Variability and Uncertainty in Energy Systems. No, energy systems. So there's more than one. There's been a focus here and in general in these meetings in the past on power systems, operations and planning. Now it's an important question, I'm not denying that. It's also the focus here, but I want to kind of remind us as a workshop that there are many other systems out there. There's the gas and fuel systems, for instance. There are multiple users out there and so multiple concerns. So you might pick on a range of concerns thinking on the operational timescale. So you've got the day-to-day concerns, grid management, plant scheduling. Equally well, you could be thinking, if I'm operating an oil platform, I might be worried about forecasting when that hurricane's going to hit. So there are a bunch of day-to-day operational problems there. Stepping back and thinking a little bit longer, you might start to think about what I've called the trading timescale. So you might be thinking about month ahead, you might be thinking about year ahead. There are long-term wholesale energy contracts that people buy and sell at extended range. You might be thinking about maintenance planning, several weeks in advance, scheduling that ship to come and service my offshore wind turbines. You might be thinking about resource planning in the medium term. How much hydropower can I use safely while still making sure I've got enough to get to the end of the winter? Think a little bit longer again, might think about in terms of strategic questions. So characterising supply and demand patterns, understand the impact of climate change if we're thinking next 20, 30, 40, 100 years. And again, you might be thinking more about statistics of extreme weather, extreme disruptive events, be that extremes in themselves, so storms or heat waves or something that's unusual weather, or simply something that causes an extreme on the system that you're bothered about. That doesn't necessarily need extreme weather, it just needs some moderately unusual weather to hit your system in a particular way. So there are a whole range of questions there, and I'm going to sort of wander through them a bit in this talk. Based on the sort of the title I was given, or sort of was on the workshop thing when I was sort of told I was talking here, I think I was offered a talk, whatever it was. There was a title that was next to it. I felt it would be helpful to give a bit of background about European weather, what it is we're forecasting. The main part of this is then going to be linking this to energy impacts and going through very quickly some of the ongoing work in the Met Department and more broadly at the University of Reading that I'm involved in. So, European weather. As far as I'm concerned, the weather in Europe is dominated by the North Atlantic storm track. Now everyone's familiar with kind of the weather forecast. You know, you get those low pressure weather systems that come across the North Atlantic and bump into Europe. If you imagine kind of the average path that they all take, that's the North Atlantic storm track. When I'm talking about a storm, it doesn't have to be a particularly extreme thing, it doesn't have to be particularly bad or anything, it's just these low pressure weather systems, these cyclones, propagating across the North Atlantic. That's what I mean by a storm. Now these storms form as an instability on a temperature gradient. So on a planetary scale, we're getting heated at the equator, cooled at the pole, we're sort of gaining energy at the equator and losing at the pole on average. These storms form as part of the instability that's formed because of this temperature gradient that's constantly being restored. Obviously it's rather more complicated now, but at crude level, that's the basic mechanism. It's an instability on a temperature gradient. What the storms do is they mix away the gradients, so there's irreversible wave breaking, they mix away the gradients, and in doing so, in terms of weather, they're associated with strong winds, warm temperatures, wet westerly flow. So warm, wet and windy if you're in winter. And the typical length scales involved were these storms are about 1,000 kilometres in size, they typical lifetimes of about a few days. They propagate eastwards around about 10 to 20 metres per second, depends on the exact storm. So here we have a little picture taken from a paper. It's actually looking at European flooding events, or flooding in the UK. I think this is an example of a flooding event that happened just here in Carlisle. What we have here is, this is the means of a pressure. You can see the low pressure weather system. You can see the southwesterly flow on its flank. This colouring shows a region of strong surface winds. What you have here is a picture of specific humidities. This is the moisture content of the atmosphere. So what you have here is a tongue of warm, wet air being evected up out the tropics, and essentially in this instance, it sort of sits fairly stationary for a little while over that region of the Lake District and causes a whacking great flood. But in general, what you can imagine is these storms are bringing along these warm, wet, moist air coming up from the subtropics. And I can talk ad nauseum on the formation of storm tracks. It's where my background is. These storms also transport angular momentum, and this is important because the way the waves break, the way these systems break, transports momentum around the atmosphere. And this is closely associated with a phenomenon called blocking. So people may have come across anticyclones, they've talked about jet shifts, that kind of thing. All these phenomena are all related, and they're all intimately connected to how the storm track works. What you have is if you get a blocking anticyclone, you tend to be associated, in the UK, it'll be associated with weak, cold, dry easterly flow in winter, so dry, still and cold. So this shows a typical blocking pattern. Here we have a high pressure system sitting over the UK. What you see is there's relatively low wind speeds, so the winds are enormously low. And if you look at the temperature anomalies, what you can see is that this flow that's going anticyclonically around the UK is bringing down cold temperatures from sort of in the interior of Europe, bringing them out easterly over the UK. And I mean, there's all sorts of discussions you can have about that. But one feature of these blocks is they tend to be slightly larger scale, and because they're larger scale, they tend to, there's reasons of the way they interact with the background flow. They tend to be quasi-stationary. They can sit around for an extended period over a single region, whereas the storms tend to rip through pretty quickly. So the point of this is that these large-scale features of the circulation grossly control the day-to-day character of the weather. They control whether it's rainy or whether it's dry or whether it's still. They sort of have that dominant day-to-day control, if you like. And Chris Stan and myself looked at weather typing to look at the wind during peak demand problem on the basis of this kind of just thinking about what kind of weather would produce it. I'm not going to talk about it anymore. I've talked about it previously at these meetings. So if you're a weather forecaster, what's the typical problem you're faced with? You have some analysis of what the current day situation is, what today's situation is, based on observations, based on satellite data. You then write down your weather forecast model. So in doing so, you chop the atmosphere up into discrete little chunks, so grid boxes. Each of those grid boxes, you write down the fluid dynamics equations, so based on Newton's equations, Navier-Stokes equations. You write down that in discretized form. You can write down within each one of those grid boxes a series of parameterizations to represent unresolved physical processes that are happening within the box. So that'd be cloud and moisture processes, latent heat, condensation, surface energy, momentum balance. You write down all these physically based equations, and from that you can stick your initial analysis in, run it forward in time for time stepping wise, and you produce a forecast a few days in advance, let's say. And there are many ways of assessing how good or bad a weather forecast is. A lot of these tend to be Eulerian in basis. So I'm worried about what the weather does in Cambridge today. I'm not worried about sort of the general pattern of features. I'm worried about it on a point basis. I want to know what it's doing here. There's a whole literature. I mean, I've given two very simple diagnostics there. Root mean square error of wind speed at a point, for instance. There's a whole literature on how you evaluate a forecast on a point-by-point basis. What I've done here is just to show a slightly different perspective, and to come into doing something reasonable is taking a Lagrangian approach. So here what I've done is, actually someone else did, identified the centre of a low pressure weather system and watched its progress as it goes through the forecast. And what we have here in the black line is the analysed storm track, the analysed path of this storm. So it goes from sort of over North America, goes forward in time for about 6 days and ends up somewhere over Scandinavia, whatever that is, Poland. My European geography is not great. And what we have here, the different colours are different weather forecast models from around the globe predicting that storm forward in time. And what you can hopefully see is that the paths agree pretty well for the first 3 to 4 days. After about that 3 to 4 day window, they start to spread out. So what's happening there is there's it's an initial condition uncertainty problem. Essentially, you're starting from some guess of where you are in this very high dimensional phase space. You have a best estimate of where you are, and it's probably not quite right. There's probably some error in it. You're then running that forecast forward. It's a chaotic system. The errors tend to grow with time, so your error in the future is bigger than your error was at the start time. And that's sort of the dominant source of error in a couple of days ahead weather forecast. So one strategy to deal with that is something that Pierre talked about a lot in his talk, is the use of ensemble forecasts. So here, instead of just taking one single best guess of where we are in the current day, we take a number of guesses based on our knowledge that are all consistent with our knowledge of the present day. They represent our uncertainty of knowing where we are now, and you run a whole set of these models forward to produce an area of phase space into the future. So that, and then the spread, or what you find is the spread of this tells you something about how confident you are in your forecast. What you also find is that you take the average of the ensemble members, you tend to get a better forecast than any single model itself. Sorry. The ensemble mean does better than the best a best forecast model, any single best forecast model. And as I said, the sorry? Over time, yes. This is over, yes. So if you have, you've got a choice. You can either increase the number of ensemble members you have, run more and more simulations, or make one model better. In general, that collection of models, if you average over them, will be better than the equivalent best model, if you like. Obviously, there are trade-offs there, but in general, that's I think a fair statement. So for instance,
the single best model is not selected retrospectively.
No, not in this instance. No, yeah. Otherwise, yes, potentially one of them could be better, but it will be a different model each time that will be better.
Yeah.
So, I mean, this opens a whole can of worms of how you verify a probabilistic forecast. In general, two measures are often considered: the variability, the ability. So, if a model predicts event B given the starting state A, then does that match? When you look in the observations for when I start in state A and move forward to future time and get B, does it occur on the right number of times? Does it occur with the right frequency? So there's a probabilistic evaluation of how well the model's probability represents the real world probabilities, or the real world occurrences, frequency of occurrence. You can also got a question of resolution. So when you're distinguishing between different outcomes, are they useful distinctions? So if I predict tomorrow that the temperature in Cambridge will be between minus 50 degrees centigrade and plus 150 degrees centigrade, I'm pretty certain to be right. I'd have a completely reliable forecast. It's also completely useless because it doesn't distinguish between meaningful outcomes. So this resolution question becomes important. Once, as before, I'm certainly not an expert in this, but there are many tools and approaches. There's ROC scores, reliability, skill scores. There's a whole literature out there. We can talk about that later. And there are a number of challenges as you go to longer and longer lead times. The slower components of the Earth system start to come into play. So instead of just worrying about what the atmosphere is doing, you have to worry about what the oceans and the sea ice and the land surface are doing as well. But again, just to give you a simple illustration, the same Lagrangian diagnostic tracking this storm. Up the top there we have a single best deterministic forecast, so it's an upgrade. It's the best model we could create at this time. The forecast, if you take this ensemble mean approach and average over many members, hopefully you can see that particularly towards the end of the tracks, so as you go towards the sort of the area over the UK, the ensemble mean forecast is much less spread and it's much closer together. And again, you'd also have information about how uncertain you are, what's the possible range of futures there. So in general, ensemble forecasting helps. The key problem though is, I think for an energy community, is how we link this to facts on the ground. And this can be because of interaction with local topography. So obviously the UK has a lot of mountains in it when you actually look at it. So how the large-scale flow interacts with topography, and also how it interacts with a particular system that you're bothered about. In this case, these are the wind farms installed over the UK. Or you might take it a step further and how that interacts with a particular transmission or distribution system within that. So the question is how you get from these very broad pictures of where the storms are and where these blocks are to impacts on the ground. So one of the tools that gets used a lot for this, and I get a little bit frustrated with at times, is this issue of dynamical downscaling. So essentially you start with a coarse grain weather forecast over a big region, and you then use that coarse grain to drive a finer grain model within it, and you then take that finer grain model and drive a still finer grain in, and you zoom in progressively on the zone that you want. So for example, the Met Office use this operationally. So globally they forecast at about 25 kilometres. They then downscale over North Atlantic and Europe at 12 kilometres, then over the UK at 4, and there's actually a system over the southern UK, so you can tell which areas of the UK are important, at 1 kilometre. So,
getting more data.
What do you mean without getting more data?
Observation. And they do this.
They'll be the same. Sorry, what do you mean more observations?
Are they simply not extrapolating but interpolating the model?
No, it's not. It's not interpolating the model. You take
finer detailed data. By observations.
I'm unsure exactly what stage they're simulating the various observations. Essentially, you're taking the output from your coarse grain model and at the boundary of the region, and then you're running another freely evolving dynamical physical weather model within that, and taking the boundary conditions on the larger scale.
Without taking any input from anywhere else. So I think Sam's point is, do you take extra information measured at a more local level?
I'd be lying if I said I knew. My guess is probably not in a large scale. You would assimilate as much as you can at the first step, would be my guess. The point being, though, and this is the point where I get a bit frustrated with it, not so much in the weather forecast context, because that seems legitimate, but when we get to one of the things that's that's talked about a lot is downscaling reanalyses for wind resource assessment. So for people who aren't familiar with the reanalyses, you can see it as an optimal combination of a weather forecast model and all the observations you've had in the past. You assimilate the two together in an optimal fashion. Again, a whole literature on that, don't ask me to describe it all. We assimilate it together in the optimal fashion, and it recreates the history of what circulation has done. Now, typically the latest generation of those are around about 50 kilometres at a global level. So, obviously we want to know what wind farms are doing in the UK, so one of the tools that people talk about a lot is then downscaling that to get more detailed data over the UK, let's say 1 kilometre resolution over the UK. That has a lot of positives, because it can add important spatiotemporal detail, and also there are some processes that happen at finer scales that are not resolved directly by the global model that can be resolved by a smaller scale model. For example, sting jets. If you're really bothered about damaging wind gusts, then downscaling has some legitimacy, or certainly has a big use. The negatives are that it's very costly to do for any extended period, and there's no guarantee that if you just downscale a short period, that short period is representative of the longer term climate. And if you're not getting the long-term climate right and understanding all its variability, then your downscale, however detailed it may be, will underestimate the total range of outcomes that are possible. So it's a trade-off between length and detail, if you like. And in any case, even if you get the 1 kilometre detail, then often you still need to link that to an impact on the ground. How do you relate a 1 kilometre box to what's happening at your wind mast at this point within that 1 kilometre box? It still remains a challenge, even if you do that downscaling. So, just to highlight this dangers of these short records, one of the sort of poster child modes of variability for atmospheric variability in the North Atlantic European region is the North Atlantic Oscillation. And in its positive phase, you get more storms coming into Europe, and in its negative phase, you get less storms coming to Europe, broadly speaking. And what we can see is that affects the PDF of wind speeds over the UK. So this is hourly mean wind speeds taken from an observation station on Great Dunfeld near Blackpool. Here we have wind speed against relative frequency of occurrence. If you just look at the blue curve, that's when you have low NAO events or negative NAO events, and the red curve is when you have positive NAO events. And what you can see is the curve shifts, and we kind of ran that through a simple turbine model, and you found you can get about 10% difference in your mean power output between this NAO high state and NAO low state. So if you're looking at a long-term record of the NAO, this goes from 1900 out to 2010, what you can see is there are extended periods where you're in the low phase and extended periods in the high phase. So if you were to pick a climatology based on just a short part of that, you might be substantially misestimating your actual climatology. So that's why there's a danger of relying too heavily on just downscale and say, just give me the numbers out of the downscale. I just want to know what it is at this point. You need to understand this long-term variability. And that means you need to interact with a different set of data sets. So what we try to do is we want to ask what can these coarse grain reanalysis data sets give us directly, thereby avoiding this computationally expensive downscaling. And what we've done here is a site-by-site comparison between, here we have some mass data for a range of Midas mass over the UK. Here we have the interpolated wind speed from our data set. What you can see is that, I mean, if it was a perfect fit, everything would lie on that one-to-one line. Obviously, you can see some sites are overestimated, some are underestimated. But once you start averaging things together, so this is a logarithmic scale now, we're taking a UK average and we're comparing, sorry, the axes have changed. It's now the mast on this side and the rain analysis on the y-axis, what you can see is that there tends to be a much better fit. This is actually a remarkably small number of points, and those that are there are typically associated with stations that are in complex topography, high mountains, that kind of thing. So you can kind of understand why there are problems, because that orography is not resolved in these reanalyses directly. So general rules for using these reanalysis data sets, and where there's sort of a growing community in the energy community who are using them, my comments are that it does not capture small-scale turbulence. It just can't. It's just not there. It doesn't have the wherewithal to do it, or the detail of these local topographic effects within 1 kilometre boxes. What it can do is it can capture significant amounts of the variability on timescales greater than a few hours and spatial scales greater than a couple of hundred kilometres. So if you're looking at national wind resource on day-to-day levels, it's probably a pretty good bet. But it's a complex validation, so please ask if you want more details. But rule of thumb, few hours, few hundred kilometres, you've probably got something that's worthwhile. It's telling you something, there's information there. So what I've done so far is just to talk through some meteorology relevant to European weather and these weather prediction models and reanalyses. So what I want to do is just kind of illuminate some of that with some examples from what we've been doing at Reading. The first project, I've put Dirk's lovely face up there so you can all find him in the coffee break, with National Grid, looking at wind generation in UK regions. So we've divided the UK up into grid boxes around about the 200-300 kilometre grid scale, the scale that this reanalysis has useful information on. And we're looking at high wind and low wind events, for example. So here we have the persistence of low wind in regions 2 and 5. Here we have 2 is in the southeast, 5 is in sort of central southern Scotland. What you hear is have the persistence time of a low wind event and the below some threshold. Here's the probability density. You see is that for any individual region it has there's a reasonably thick tail, but if you compare the two regions together, the tail is rather thinner. So we're trying to develop some of these statistics. I don't think the details of the numbers here are the key here. We're trying to develop the statistics of these numbers in a bit more detail with National Grid. Another example is thinking about ramping and cutout. So here we have on a UK level now, we have time window across the bottom, so time window of a ramp, so from how many hours it is between the peak and between the top and the bottom of the ramp, and the threshold amount of power change. So for example here, we have at 100 times a year there are power ramps of more than 40% of the total installed capacity in timescales of less than or equal to 6 hours. So we're trying to quantify how big the potential ramps are, again using these kind of data sets. The next steps, we're hoping to expand this to looking at day-ahead forecasting, sub-regional extremes. And I'd actually start to like to look, whether we'll do it in this project, but start to look at the link between this and temperature in terms of understanding, as Paul was talking about, how it's transmitted around the region and what the transmission requirements are. A connected project is Dan Drew, another smiley face, looking at how you take the wind estimate, a local wind estimate, and transform that into the wind power for a particular wind farm, particularly offshore wind farms. So Dan is working on that, active at the moment, so please talk to him about that. I also have a PhD student, Kieran Lynch, working on looking at monthly scale forecasts. So there's a lot of use in the industry of trying to use weather forecasts a couple of days ahead, but essentially beyond that, people start to think it's just like a climatology. It's just, what happened this year is just what my expectation for what happens at the end of March, at the end of, where are we? April, the end of May would be the same as the average of all the previous years of May. That's how I base my expectation of what the future is. What we're trying to do is update that expectation using a monthly forecast system, an ensemble forecast system. I'm not going to dwell on the details, but the initial results are quite encouraging that there is some skill in these forecast systems at 3 to 4 weeks. And we're exploring with one of the big 6 energy companies how you might use it for energy trading, for risk management, and also maintenance scheduling. Seems to be another issue that they're bringing up to us, of how you use this kind of information. One more problem, so there's 2 more examples. This one is an example of, one thing I want to delve into a bit more is just thinking about, rather than thinking about just wind and just solar and just demand on their own, is starting to put those pictures together from a meteorological context. So one question that was asked by Poiri actually was, what about Scandinavian hydro versus UK wind? There's this talk about growing interconnections, using the hydro to kind of buffer the low wind events. So we set up a very idealised thought experiment. What happens if we connected UK wind to Norwegian hydro and use it to meet the combined demand of the entire region under future scenarios of UK wind as you get more and more wind? And we wanted to know how would climate variability affect such a system? And the answer is quite a lot. If you think about this poster child of variability, this NAO, you find that the NAO is correlated with precipitation, with temperature, wind speed, and with temperature over the whole region. So if you have a low NAO winter, you tend to have dry, still, and cold conditions. So that means your demand is high. It would mean you've got low wind, so high demand net wind. At the same time, your Norwegian hydro is running down over the winter, and you have to wait until the snow melts before you get recharge on it. So you've got to last a little bit longer on the same supplies because they're likely to melt a bit later because it's colder. So there's a kind of triple whammy effect, and as you start to put more and more wind on the system, obviously you're increasing the range of the demand net wind, and you find as you go to future scenarios out to 2035 in the UK wind, it would suggest that there'll be a 6-fold increase in the NAO's effect on demand net wind, all other things being kept equal. So it suggests that if you're in this kind of situation where you get to the end of winter, you've run down your reservoir stocks, you've now got a decent forecast for what's going to happen for the coming month, that would have implications for how you would manage and how you would price the remaining water in your reservoir. So there's questions for management of the resource there, and I think there's a real application for advanced forecasting at the multi-week timescale here for updating your expectations. So this paper, I'm having a bit of a fight, but it's gradually going through in energy policy, if anyone's interested. Thinking now towards the future, both in terms of the science and in terms of sort of practicalities, we've got another PhD student in October working with the Met Office, looking at using the latest IPCC models to understand the impact of future climate on energy systems and energy system scenarios. So here we have a picture of, this is kind of the average path taken by these weather systems. These are the storm tracks. There's storms form over North America, and they tend to move on a southwest and northeast trajectory towards Northern Europe. This shows, from the latest set of IPCC simulations for a fairly extreme scenario, the change in the storm track over towards the end of the century. So you can see there's slight intensification of the storm track over the UK, possibly a poleward shift, possibly a tightening. It's sort of quite a complex tripole pattern. There's been a lot of work going on in my department trying to understand what the causes of that are and how robust that change is, and that's a complex subject in its own right. But the question is, how will this kind of thing affect demand, supply, and energy resources in the future? So I'm just finishing now. So what I just want to, that's good that. What I want to say is that the climate problem is a complex problem, and there's entire workshops here at the Newton Institute just on understanding climate and how we deal with the statistics of that. It's a complex set of uncertainty from initial conditions of the slow evolving components such as the ocean, and the boundary condition, which is external forcing such as CO2, and also model uncertainties, the parameters and the missing processes within that. What I want to particularly highlight is not to say that there aren't massive uncertainty in the energy side as well, but what I want to highlight is that towards the end of the century, the emission scenario dominates. That's what controls the overall response. That's one of the primary determinants of the overall response is down to the emission scenario. You can tell whether you're on high emissions or low emissions. When in the mid part of the century, most of the uncertainty in the climate predictions comes from a mixture of model uncertainty. Okay, models aren't great, but it comes from a mixture of model uncertainty, but also the natural variations. So in terms of the ocean, it's an initial condition problem. It's what state is my ocean in now, and how is it going to evolve over the next couple of decades? There's much longer timescales involved. And this is why doing detailed climate predictions out for this part of 20, 30, 40 years into the future is actually a lot more difficult scientifically than doing them towards the end of the century. Perverse, but it's true. So, anyway, there we are. Summary, I think there's a lot of opportunities for better use of meta in the energy sector, from process understanding, from forecasting, from hours out to decades to centuries, and I've tried to give a bit of a flavour of some of the projects going on at Reading. I was trying to scratch my head and think about how this connects to thoughts for sort of a workshop such as this. I think there's a real difficulty of connecting this to the energy impact, connecting to point local data, so a particular mast or a particular wind farm, and the high freezing properties, and how we regenerate them from this large-scale data that we know something about in the weather forecast models. How do we get that back to doing the detailed minute-by-minute, 15-minute interval wind forecast, for example? Downscaling is useful, but you still need to understand what the large-scale uncertainties are. And I think there's a lot of opportunity. I'd like to see more joint statistical physical approaches. I think that's where the real mileage is, rather than it just feels a bit dissatisfying to me as a meteorologist when statisticians kind of ignore the physics and just go on to produce a time series model. Well, so this is it. It's how you combine the two. So yes, better linking the models. Please, let's not just think about the power system. Let's think about other energy systems. There are other policy and operations. Yeah, these are more social issues, but there's energy, food, water nexus. There's a lot of connections between these in terms of how they're going to change and how they impact each other. I suggest that's sort of a big topic. And also there's this issue of unburnable carbon. So at the moment, all these fossil fuel companies are valued as if they can burn all this carbon. But if we're actually going to stick to a 2 degree above normal, 2 degrees above pre-industrial target, there's no way they can burn all that carbon unless it all gets sequestered. So there's a question of how you value companies. So it was recently in the news, but it's kind of growing up the agenda. There's a big issue there. And I'll shut up now.
I would like to mention that if you open the book of Wilkes, which is about statistics in the atmospheric science, I think he explained in one sentence that it's more meteorologists that historically kind of disregarded the statistics. So I think we have to be fair there.
I'm not trying to lay blame. I'm just saying we need more.
But in terms of, I think a lot has happened over the last few years, and there's been a number of initiatives for getting these communities closer. So I wouldn't be pessimistic about that. And I don't know if you felt that in the UK.
For discussion. So and next question. Maybe it's for discussion, not now. For now, so question.
A quick question. You did say that the main source of error in short-term forecast comes from initial conditions, and that's why ensemble forecasts are so powerful. But I've also heard it said that the problems can arise from not capturing these processes at scales less than the grid scales that you're using, and that's why meteorological models are so bad. For instance, it's modern blocking, which is obviously very important to us. And the way forward here is perhaps to think of using not just straight physical models, but physical models combined with sort of stochastic processes. And
yep.
Do you have any comments there?
Yes, there certainly is a lively debate on whether a climate model should be stochastic or deterministic. There were seminars on it this week in Reading, actually. So it certainly is an active debate on how we deal with that. My impression was that on the weather forecast scale, blocking wasn't doing too bad. I'm not an expert on that, but that was my impression from being in a community of people who know more about it than I. On a climate model scale, there is certainly more of a problem. They certainly underestimate blocking, or they misestimate it. Sometimes they overestimate, sometimes they underestimate, but in general it's underestimated. So yes, there are certainly problems, and depends on what features you're worried about. If you're worried about the fine scale features, be sting jets, for example, and these very intense wind regions in the centre of storms, then yes, you undoubtedly need a very, very, very high resolution detailed model to capture it. And it doesn't matter what, it doesn't matter how many ensemble members you have, you won't capture it unless you have the resolution to be able to do so. So it's one of these things, it's how do you verify a forecast? What is it for? How do you decide which one's good or which one's bad? It's very subjective. When I'm talking about it, I mean on the large scale. I tend to define that's where I think the most power is. I'm always a little bit cautious about doing the point-by-point thing myself. I'm aware people do it, but then which processes dominate?
Sure.
It's very quick. So, just think of an example. In the Pacific Northwest, they had a terrible disaster because they didn't understand the regulation reserves they'd need. And they wouldn't have needed a point forecast, they would have needed a power spectral density, an estimate of, and they would have known what resources they needed to balance, to compensate. So there'd be real-time feedback to get rid of this disturbance if they knew the power spectral density well in advance to get the resources available. And I think a point, they don't even want an estimate of the actual variable, they want the statistics. That's what when you get down to less than 5 minutes, it's, getting estimates of the power spectral density would be the dream. That's my conjecture.
Personally, I think there's a role for both. I think it depends on exactly what your problem is. If you're worried about the day-to-day balancing, then you need still need to forecast. But if you're planning it, yes, you need to have the statistics in mind.
Okay, thanks again.